Let's kick it off for today. Welcome everybody for the morning session. We will have Professor Edzer Pebesma as a keynote, and yeah, maybe Edzer, you can introduce yourself better. Yeah, I think all people who work with R, they're very familiar with Edzer work. Yeah, but please, Edzer, floor is yours, and let's start with the talk.
Okay, thanks, Milutin. Thanks also for inviting me and to this interesting workshop or hackathon. I would have liked very much to participate in person, and I've been puzzling quite a bit to get this done, but it is in the midst of our teaching semester, so there's always trade-offs to be made. So I was asked to say something about openEO. I joined Patrick his keynote yesterday and heard what he said. So I'm trying to not duplicate it. I'm very grateful that he took a lot of that. So I'm associated with the University of Münster and working at the Institute for Geomathematics. I'm an ordinary member of the R Foundation. I'm also involved in OpenGeoHub as one of the management board members. And I'm involved in openEO as one of the initiators and participant in several projects trying to get things going, as Milutin was. So first of all, I'm going to talk about open science and what is it exactly. And roughly, if I think of it, it means that beyond sharing scientific papers, which we try to do hopefully using open access journals and so on, we also sort of in papers we describe what we do in terms of words and equations and so on, but that we in addition to that also share how it was done by ways of sharing all the data that we use. There are the FAIR principles really about data sharing, but also that we share code that we develop to get things done so that the results in the paper, the figures and the tables, the numbers can be easily reproduced and also reused, but also that findings can be scrutinized, right? It's not only about redoing, but it's also about building new work on top of existing work that is easier if somebody shares code. If you do that, your citations will dramatically go up, but also finding out what happened, and if you don't understand things, that you can go into the detail, meaning go into the software that was used and see what was going on there. So for that, you need to use open source software so that licensors are not obstructing reuse, that you can actually do that. There are not sort of unnecessary costs like paywalls for scientific papers and so on. And in addition, sometimes you need to make sure that versions of software are all documented and guaranteed. And it can be convenient, it can be a good idea sometimes to additionally share also entire runtimes. That means virtual machines, for instance, Docker images, that contain the entire software stack that you used in order to make sure that in 2 years' time, software evolves and that things done with the new software are not identical. Then you have something to fall back on. That is never a sufficient thing, right? Docker images are binary, are basically executables that you share. So if somebody shares Docker images and says, here is my software, like the Apex that Patrick mentioned yesterday, that's not enough, right? It can be full with closed source software, so be careful about doing that. But the problem is, how does this work when the data used is too large to download? So that's one problem. Another is, of course, if somebody used a supercomputer or used 100,000 CPU hours, all kind of things that you cannot afford. But one thing that we now look at is sort of too large data sets. For that, we have cloud processing platforms. Now, suppose that you carry out a land cover classification and you use a certain method for that. You use the same data, you fix a method, you fix a data set that you're going to use, and do this in Google Earth Engine and on Sentinel Hub, right? You're crazy enough to not just stop after doing this once, but you want to try out this thing on another platform. And then you find that the results are slightly different, right? And you wonder sort of where does this come from and what do you do then, right? The problem is how to continue. If these differences are too large to ignore, then the problem is that how are you going to verify which of the results is the one you should prefer or is what you think of as the correct one? And also, where do you go to ask what is going on, or what should you do next, sort of with this problem, sort of who to consult. This issue is that both platforms can use scripting interfaces. So sometimes people think that makes them open source, but the software actually doing things is the sort of the backend processing systems. They are both in closed source. So you could look at, one thing is already trying to find somebody who compares the two scripts, the Sentinel Hub script and the Google Earth Engine script. And then the question is, who is willing to do so? So you're a little bit lost there in terms of figuring out how to continue. The data structures we look at are essentially data cubes. So we have images. We look in Earth observations, images and time series sequences, time sequences of images, and images are typically multispectral, right? So this is the canonical data cube. Of course, data cube are just multi-dimensional arrays where array dimensions can reflect all kind of things, space and time. There can be multiple time axes. There can be dimensions that are associated with vector geometries, vector data cubes, and so on and so on. But this is a model that is very useful for Earth observation data. It also applies to model data. Actually, model data like weather or climate data, ERA 5, CMIP 6, typically even fit better these data cubes because they're computed on a data cube. Where Earth observation, you have this problem with all the tiles that are scattered and all the coordinate reference systems and so on. And those are things that in computed in sort of predicted modeled data cubes that can be sort of resolved before, and you get regular time intervals and so on. Yeah, for Sentinel-2 you have regular time intervals, but can be 5 days, and you want to work with monthly and so on. There are these kind of issues. So the traditional way of Earth observation data, let's say 10, 20 years ago, was that you would be in a research group that would download data and have these data typically somewhere, or you would download them yourself, then mosaic, stitch together images, do some corrections, radiometric corrections or something like that, possibly regrid things, then do something with times in order that you get some kind of common time basis. And then you run an algorithm, a time series algorithm or whatever, and collect results. Initially, we would sort of do this, we publish what we did, the algorithm and the results, the images, the algorithm preferably displayed as mathematical equations, right? Things that people still have to puzzle how to implement them. Basically, this is what we need to do for reproduction, right? So this is the whole sort of process is essentially needed. Nowadays, with cloud platforms, of course, the download is gone because the data are there already. What we then had was that all kind of systems would come up like 10 years ago that would, allow you to do things with image collections that were in clouds, and everyone would have its own cloud and data organized in its own way in a certain cloud structure, and have a set of users that did that. And each of them would have a certain interface, so that if you would use the Sentinel Hub, for instance, from Synergize, you would write a script, but that could not be used on Earth Engine or on the JRC infrastructure or on the Vito cloud usage and so on. So everyone would have their home built systems, and there was also very little sharing of software when these things were not like public interfaces, because these systems typically grew incrementally with a lot of PhD and postdoc work, and not structural software engineering and so ad hoc, and so there was very little code sharing and a lot of mystery going on what exactly went on in these studies. Yeah, so that was bad for everyone. So then the idea came up to centralize that, and basically to say, well, essentially all these backends, they do pretty much the same thing, or at least they have a lot of in common, and maybe all these commonalities we can describe, we can formalize through basically processes that we then give a certain name, and for which we give certain parameters and have it work. And so that is when the idea of an API, an openEO API, came up in 2016. And if you have that, you can basically access all these backends in the same way. You only have to write client interfaces once for every programming environment, be it R Python or web-based environments, or Julia, Quantum.js, and so on. Right, and you basically serve all these users in it at once and be able to compare things. This model is not new. This already started 30 years ago with GDAL. You have learned on Monday a lot from Giuseppe Amatulli about GDAL and how it works. And GDAL is still there, probably in all these systems, like, you know, it's probably all in ArcGIS and in Google Earth Engine. We don't know, but it's pretty sure that it's there. And it kind of solves the file formats problem, right? Writing and reading files is not an issue when you're in R or in Python. That is an issue of GDAL. And once you've done that, kind of you don't have any problems with formats anymore. So you can write all these different systems and softwares and so on that no longer have to worry about adding some kind of new data format, because if GDAL adds it, then the next version of your software also has it, right? So this is extremely convenient in that sense. And these advantages kind of go up. Here's a graph from the R package ecosystem, where a package SF that was for 20 years ago, a package SP is now replaced by SF, which basically links to these libraries, GDAL, Proj, and Geos, and as to geometry to do I/O and geometric operations, and so that in principle everyone wants to do, but all R users that write packages don't want to deal with the complexity of linking this software, so they basically depend on SF to do that. So there are now nearly 1,000 packages on cron that do all kind of spatial stuff that rely on SF to deal with the file I/O and the geometric operations, right? So this added interoperability effect kind of goes up, right? And you see the same thing in Python, where all kind of packages use GeoPandas, and GeoPandas uses a number of lower level packages, and another package uses GeoPandas to take care of representing vector data in tables in a certain way, right? That is very convenient. So these kind of things work very well in software ecosystems. In the context of openEO, what does API mean? So I'm not going into detail in that. I did in the summer school last year a little intro where I had everyone sort of write your first API, basically REST API, to sort of take off the magic of it, because there really is no magic. It's just sort of computers talking to each other. It's a specification, right? It is specification, basically how the internet works. Everything works over API. Anything we do now sort of works through APIs, clients and servers and so on. OpenAPI is an industry standard for defining APIs, right? So there is a way, a standardized way how you write these things. And if you do it that way, there's an incredible amount of tooling, and it becomes extremely easy for software developers to program against these APIs, right? Because they are a standard documentation. You can look up things, how they work easily, all automatically generated and so on. So if you have something that follows this OpenAPI industry standard, then you make software development much easier. In addition, all the data science languages that we use, so the problem is that you're not, if you would write something entirely in R or something entirely in Python, like if you think of PanGeo, which is basically X-ray task, then that's a great system and so on, but it's Python constrained, right? So they have the problem that some people do some things in R or in Julia, and they have a problem to connect to those because everything is in a Python silo. With an API, you don't have this. All these data science languages both basically have infrastructure to easily write clients or servers that conform this API, right? So you could, and that's actually what's being done. So these clients are available and try to speak a native language, so to speak, connect to how people are used in R, are used in Python to deal with problems and how to program, how to solve problems. There's a web editor that uses the JavaScript client that Patrick showed yesterday, and you will probably see later today. And new clients are pretty easy to develop. New backends are also relatively easy to develop, and that is also happening. If I say openEO API, there's actually two things that are kind of chunks of information. One is that the real API that does all the bookkeeping, that does things like authentication, that does things like describe the processes, describe the capabilities, that does account management, that does the discovery of data, process discovery, and so on, and handling of batch jobs. So all kind of bookkeeping things. It defines the endpoints of the API. So that's mostly a bookkeeping thing that is not related to sort of what you do with Earth observation imagery. And the second thing is the processes. That is here process.openeo.org. is a specification of all kind of processes. There's a few hundred of them that you can apply to data cubes. Yeah, so there are all the mathematical processes like absolute and so on, sinus, cosinus, all the standard mathematical functions that you have in all programming languages that you can also reuse, but also a number of them that are specific to data cubes. Add dimension, aggregate space window, aggregate temporal, kind of aggregation processes that you would apply to array dimensions to do meaningful steps later on. And so this basically gives all the building blocks of a programming environment where you can make arbitrary complex expressions of things, essentially the same way that you do things when you write Python scripts or R scripts or something like that. You write essentially a set of expressions that at the end something comes out, and the whole set of expressions can be represented by a graph structure, which is essentially a computable expression, and that is what is happening here. So what openEO does is create this graph, and then that graph basically describes what needs to be done, and then you say now do it, and then it does it, right? So a session typically works that by connecting to a backend, and the backend may have different capabilities, right? May not have all processes available. Then you may have to authenticate, depending, if you are connecting to a public platform and want to compute there, you need to be billed for that. You look up the available collections, you look up the available process. These processes are all free. Then you define a problem, you select collections, you define typically spatial extent, temporal extent, and band. So what's the data you're going to work on? And then you define the processes on those selected imagery and do that. And maybe you have an opportunity to check billing, what is it going to cost? And then you're going to submit the job and download results and view the results. And only step 8, when you say step 8, download the result, actually computing is triggered, and the results are being produced. And so this is the sort of lazy evaluation. Everything before that is essentially free and doesn't take time. You can do things in synchronous mode and asynchronous mode. So you can submit batch jobs and later on check their status and see whether it's done, right? If things take hours, you're not going to watch your screen for hours typically. So the question is, who pays for all of this? Well, the software development so far has been paid for, luckily, by the European Commission and by the European Space Agency mostly. And that is very fortunate, and I think also very clever for them, because in the if everyone does something else, then you never see good things happening for everyone, right? Problem solved. So if you run your own hardware, on your own hardware that in your own managed cloud resources, then you essentially pay for yourself. So you can skip these authentication steps and so on, because you already control the hardware, you already logged in, right? If you're on public platforms like the Copernicus Data Space Ecosystem or openEO platform, there are 2 platforms, as Patrick mentioned yesterday, that are kind of now exist, and they're probably trying to converge. Because it doesn't make so much sense. So this is some sense of how things evolve over time. We have to see whether in 5 years there will be still these 2, or whether they will have merged in some way. And if you run on them, then you can basically using ESA's network of resources have to sponsor it in case you don't do commercial activities, then you can get a lot of credits there. You can also buy credits, right? You can also, so important to know is that on these systems, the data are available there, right? So that the multi-peta, very large data collections are available, and you actually don't pay for the storage, right? The storage is very expensive, but it's not, you're not paying for that storage. The billing process, in particular for federated cloud processing, may be challenging, right? Federated means that there will be different clouds that solve parts of your problems. For instance, because there is not a single cloud that holds all of the archives that you're addressing, right? So if you want to combine ERA 5 and Sentinel-2 over a continent or something like that, how are you going to combine these 2 things, right? So that an approach is there to do this with federated cloud processing. Yeah, where to go with questions? If you don't know, if you got stuck, so of course try the person who stands next to you. The next thing to try is the user forum. that is here. There's a user forum that was set up for openEO platform, and I think currently for the CDSE you would also go there. I don't think CDSE has set up a new user forum. There is then, if there are software related things, you want to use particular software, you find bugs or have questions about it, you can go to the GitHub repositories, find the proper repository, see here there are 65 repositories. Several of them are, of course, outdated and no longer in use, but a lot of them are in active use and development. You also see there are 55 developers involved, so there's a large number of people actually contributing and helping to get this ecosystem going. Then I want to point your attention to a very nice course that was developed by our colleagues from UREC called Cubes and Clouds. It is a very nice introduction to the ideas of openEO and getting hands-on experience. And essentially, here is my last slide. So the idea is the hope, and I think we are pretty successful in the idea that openEO brings back open science back to Earth observation research. We managed to, over the last 7, 8 years, to provide users with a platform where they don't have to worry about individual files or managing cloud resources. That was kind of reason one, right? Why is Google Earth Engine so good, right? Why does everyone want to use it? Well, because you don't need to sort of plow through hundreds of files, what you would have to do if you work with GDAL on a low level. And also about sort of the managing of cloud resources is taken away from you as a sort of setting up virtual machines and running them, managing them, logging in, and do the whole administration, paying for them, etc. Right? Those kind of things are things you don't want to confront new young researchers who would like to work with Earth observation data with. That is not of this time. Somebody has to do that, has to worry about it, but kind of openEO tries to abstract these problems away. The platforms have support from ESA and from the European Commission, and most of the implementations that work are built on 100% open source backends, right? So that is an important thing for open science, of course. There are connections to Earth Engine and to Sentinel Hub, also because they have certain capabilities that you may want to still may want to use, or you may want to compare them to other backends. There are also backends that can be run locally on your local laptop, for instance. And also a platform where analysis is based on data cubes, but integrates well with vector data and is in no way constrained to Earth observation data, as I said, and as Patrick Griffith showed yesterday in the windmill placement example, which is essentially a kind of a GIS operation thing, right? Not necessarily completely constrained to Earth observation data. So this now consists of an active and lively ecosystem of users and developers, and is sort of going well, I think. So there's many reasons to get involved, I would say. And with that, I hope that there will be an interesting day today with practical experiences on openEO and trying out things. And I look forward to your questions. Thank you. I don't hear anything, but let me see.
Thank you, Ed.
Yeah. Yes.
Thank you, Edzer. It's a very nice talk and great to see all those developments and understand a bit more background about openEO API and how it evolved and developed. Yeah, I think it's amazing thing, and so I hope it will continue developing in future as well. So please go ahead with the questions.
Yeah, I had a question. So you mentioned, you gave this example, right, where you run kind of the same process with the same data once on whatever Synergize and once on Google Earth Engine, you get different results. And it sounded like openEO kind of wants to solve this. Have you tried this? Like, does the back end of these platforms introduce some noise that even you can control? Noise, like something that you can control, or did it solve it?
So the problem is how to solve it, right? Or where the problem is basically, where does this problem come from? Or why do I get different results? And I think that because we now have openEO, we can relatively easy expose things like this. Yeah, so openEO is never going to say, well, this is the right answer, right? It can never do that. It can only say, if I send the same process to 2 different backends, here are the results, and then you could compare them. But if there are differences, we found actually differences in experiments, that very simple experiments that we did, that then we could look back in detail, and it had to do with normalization on Sentinel-2 imagery that happened on some backends, but not on other ones. Right, there is this crazy value range, I think, and then some backends would normalize that to some kind of other range.
Yeah.
So these kind of things that you figure then out, and that is very useful information to have. Also, if people are going to use these backends, that you are aware. Oh, but watch out! This platform normalizes the Sentinel-2, all the Sentinel-2 data before you used it, right?
Yeah.
So it's not a solution, but it's a way to basically discover things and then try to figure out where they come from. And in some cases, that figuring out is being made difficult because backends are closed source.
Yeah, no, that makes sense. I guess in like a dream scenario, you could like account for them, right? If you know, oh, Google Earth Engine does that and they do that, like theoretically, maybe you could control for it, but then they change it, right? And you.
Yeah. I don't think that should ever happen, or I don't think that's a dream scenario.
Are there any other questions?
Yeah, this is Giuseppe Amatulli. So nice talk. And how operational is, so how many users and which projects are running? Do you have a kind of estimation about such a statistic, let's say?
No, I don't have them. So the people that I would ask then to get these numbers are Benjamin Schumacher at EODC and Jeroen Dries from Vito. So and then there's of course the Sentinel Hub backend, where people are very well aware what the usage is, but since this is a commercial company, they may not want to reveal that. Or maybe they want to, right? Because it's advertisement and the company has layoffs at the moment. So I don't know. So this is kind of the persons who operate these backends really. And currently that is Sentinel, that is Synergize, that is EODC and Vito at the moment. So we could ask them, and it's starting up. So the CDSE operational platform is only sort of there for 1-2 years, and it's slowly growing, but we're not in the numbers that Earth Engine has, I think.
Hi, Edzer. Thank you. Tom Hengel, OpenGeoHub. What's the next big milestone for OpenEO?
Yeah, that's a good question. So OpenEO is essentially a community activity. So everyone who gets involved and has good ideas, good ideas are always welcomed, and nobody will obstruct you from doing good things. So that is, in that sense, it's organically, and a lot of things that have been done, that have got prioritized over the last few years, basically came from community involvement. One of the things that I and that also in the project that we run with OpenGeoHub that we're doing, trying to improve is to make running machine learning models easier, right? So there are some early attempts of doing this, some processes that can do a random forest regression or so. So there have been cases where we ran these, but these processes are kind of still called experimental. Like you can implement them and they have run and they maybe still run, but they're not kind of shaped in a way that we think that they will remain like this. So we would like to cover machine learning and deep learning, so also convolutional neural networks and time series neural network models in sort of a way that makes it where we cut some interoperability problems, so that we don't end up with like 50 different API calls for 50 different models or something like that, right? But try to schematize it in a good way. So that is current research, how to make that easier and then get it exposed in the clients.
Just in connection to that, I was really inspired by a little project called openML. It was kickstarted by a group also behind the MLR, machine learning in R. So I think some colleagues from Munich and also from Eindhoven. So what I like about it, that you can register, the tasks, the data sets, processes, and they kind of stay registered forever. So you demonstrate that some machine learning has some performance. And
yeah, that's a great question. So I think that is somewhat similar to what Kaggle does, right? So the registry,
yes, exactly.
data
Yeah,
sets,
but just like open source, not the commercial solution.
Yeah. So I think these examples are very good, and it would be great in the longer term to have something similar for Earth observation. The struggle or the challenge we now have, I think, where several people in my group are working on, including Brian Pondy, is to get these the generic way that people do this in OpenML, to map that onto a generic way to do this on data cubes. Yeah, and that sounds relatively trivial, but that is still a hurdle that we need to take, right? And then there's the thing about the pixel-based machine learners are relatively straightforward to map onto those, but then the convolutional-based convolutional LSTM or spatial convolutional networks are kind of more tricky because you have these neighborhood structures in space and time, right? To address.
In the Radiant Third, they had this ML hub, right? Then something happened, and I see that it's been discontinued.
Yeah.
So it is very complex, I think, right? You can see that.
So that is complex, and that has been abandoned. So maybe it was too complex. We should actually call them and ask why they abandoned it. Some of it is, I think, politics and finance, but other things they did, and that is they were looking at, and some other people picked up and continued, is catalogs for machine learning models, right? If everyone trains their own model, training is very expensive for the convolutional models. So if you want to share trained models, how do you do that? How do you describe models, and how do you find out whether you can apply them on a certain data cube or not? So that is the kind of what the StackML extensions are, sort of how to find and exchange and catalog models that have been trained by somebody that could be reusable. That is another sort of big chunk of a large challenge that is to be addressed, and would be very nice if we can integrate it. We're involved in an European project that just started that is about embedded sort of these foundational models. Yeah, so the idea that you have the complete Sentinel-2 archive, you want to compress that using machine learning, want to compress that to something that is maybe a few terabyte or something like that. That still captures most of the variability. A lot of the variation is, of course, redundant and can be compressed. That's the idea of AI compressors, which is another thing that could be needed to bring two different data cubes, very large data cubes, for instance, ERA5 and Copernicus together. Is one way would be compressing one of them and move it, sort of, yeah. So AI compressors is another topic that we are looking at. Jonas Hurst is doing that.
It's one follow-up question. So for this machine learning part in openEO, do you envision just to, or let's say, continue from the already trained model, or there are some plans to incorporate the point data or vector data and do some training as well there, or what would be the strategy or the...
Yeah, that is a very good question. Machine learning, deep learning consists of a training step and a prediction step, and in any case, the prediction step you would like to have to work on the cloud platform, but in many cases you also want to do the training step there, depending on the cloud resources you need for that, or depending on the size of the training data that may be possibly too large to run locally and so on. But you would like to have both as an option. We're also looking at this this initiative called ONNX, ONNX, which is kind of a data format that makes PyTorch, that makes Torch and TensorFlow interoperable. Sort of kind of an open way of describing or capturing trained models so that you can move them around from backends, essentially from deep learning backends. But ideally, you would like to be able to also do this on the cloud-based. And then, of course, comes the question like, how do you handle training data in, how do you make that, how do you offer that and put that in the stack and so on. And a lot of problems come up if you want to do the whole chain in a cloud platform.
Okay, thank you. Is there any other questions for Edzer? Okay, seems not. So thank you very much, Edzer.
Thanks so much. Thanks for the good questions. I really enjoyed it.